The previous video on the Nernst equation explained both its purpose and how it's used. There are, however, a few clarifications that I'd like to make. This is the Nernst equation as it's presented in your textbook. The previous video described the source of each of the terms in the Nernst equation, but you may notice that the constant 62 is a bit different from the one in the video. That is because the derivation of the equation in the video was done at room temperature. Because we are concerning ourselves with the Nernst equation in the context of cells, we will use 37 degrees as the temperature. Therefore, 62 is the constant that will be used in the Nernst equation. Recall that the Nernst equation is used to calculate the equilibrium potential of a single ion. The equilibrium potential is the voltage at which the chemical and the electrostatic forces balance one another for that ion. In other words, there will be no net movement of that ion at the equilibrium potential unless the concentrations that we've used to calculate that equilibrium potential change for some reason. The actual voltage across the membrane can be calculated by a more complex equation, the Goldman-Hodgkin-Katz equation, because it considers multiple ions simultaneously, as well as the relative permeabilities of each of those ions. Again, the Nernst equation is only concerned with a single ion at a time and the concentrations of that ion, both inside and outside of the cell, at 37 degrees. There is a term in the Nernst equation that your textbook omitted, and that is the term Z. Z is the charge of the ion that we are considering. So the voltage across the membrane at 37 degrees Celsius is 62 times the charge of that ion times the log base 10 of the ratio between the concentration of that ion outside the cell relative to the concentration of that ion inside of the cell. These are the typical ion concentrations inside and outside of a cell at physiologic conditions. I don't want you to memorize these concentrations, but we will use them in some example calculations. For example, I'd like to use the concentrations given to use the Nernst equation in calculating the equilibrium potential at physiologic concentrations of potassium. Again, here is the Nernst equation from your textbook, including that term Z for the charge. The voltage across the membrane for potassium is 62 times the charge of potassium, positive 1, times the log base 10 of the concentrations given in the previous table. 5 millimolar outside of the cell, 150 millimolar potassium inside of the cell. First, we're going to divide the concentrations. The voltage across the membrane for potassium is equal to 62 because the charge for potassium is 1 times the log base 10 of that ratio. Dividing 5 by 140, we come to 0.0357. We will then take the log of that concentration ratio to come up with the voltage across the membrane is equal to 62 times negative 1.45. We simply do that multiplication and the product of 62 and negative 1.45 is negative 89.7. Since the Nernst equation calculates the voltage across the membrane in millivolts, our equilibrium potential for potassium, using the physiologic concentrations provided in your textbook, is negative 89.7 millivolts.